Imagine, just for a second, that you're trying to solve a massive medical mystery about the human brain. Now, for decades, we've had all these tools to measure brain activity, right? But what if we've literally been measuring the wrong thing this whole time? Welcome to This Explainer. Today, we're unpacking a really fascinating piece of research that proposes an absolute paradigm shift in how we understand neural computation. We're looking at a study on NeuroByte detection, and I'm telling you, it might just change everything you thought you knew about how the brain communicates with itself.
Okay, think of the brain like a giant, world-class symphony orchestra. For the longest time, the main way we'd grade the performance of this orchestra was basically by just sticking a microphone in the room and measuring the sheer volume of the instruments. If the volume was loud, we just assumed the brain was working hard. But ask yourself this: what actually makes a symphony beautiful? Is it just how loud they can play? Or is it the rhythm, the precise synchronization, the perfect timing of all those musicians playing together? What if, to truly understand brain health, we need to stop measuring how loud the brain is and start measuring its rhythm?
All right, let's jump straight into section 1, Beyond Brainwaves, a new paradigm for neural computation.
So, traditionally, standard EEG analysis focuses really heavily on spectral power. Basically, it asks, how much neural activity is there? But this new E sub J framework flips that entirely. It argues that the temporal organization, the actual timing itself, is a fundamental part of the brain's math. Instead of just looking at the raw amount of activity, this model introduces these things called neurobytes to measure exactly when and how that activity gets coordinated. It's kind of like the difference between just knowing the musicians are playing their instruments and knowing the exact millisecond they all hit the same note in perfect unison.
Which brings us to section 2. Enter the NeuroByte, the building blocks of brain synchronization.
To actually test this whole timing theory, the researchers needed the perfect test bed. So they looked at motor execution and motor imagery, basically actually moving your body or just vividly imagining moving it. Both of these take a ton of highly coordinated communication across different networks in the brain. So let's clearly define what we're looking for here. A neurobyte is defined as a transient integration event. In plain English, it's a super short-lived window where different neural populations temporarily sync up. We're not just talking about random, isolated brainwaves. These are the exact fleeting moments when completely distributed brain networks successfully talk to each other across space and time. It is that precise second the orchestra hits perfect harmony. Now, the million-dollar question: how do we actually spot these moments in the raw data? Well, the researchers set up some incredibly strict mathematical rules for a signal spike to actually qualify as a neurobyte. First off, the normalized signal envelope has to cross a specific threshold, a z-score of 1.8. But that's not all. This spike in synchronization can't just be a glitch. It actually has to stick around for a specific duration, lasting anywhere between 30 and 500 milliseconds. So if it hits that high threshold and holds it for that tiny fraction of a second, boom, we've got a neurobyte.
Moving right along to section 3, Measuring the mind's rhythm, extracting the data.
Okay, so we know what our neurobyte is, but how on earth do we pull these tiny events out of all the raw, chaotic electrical noise in the brain? Using this dataset called the PhysioNet EEG Motor Movement and Imagery Dataset, which features these massive 64-channel recordings, they used this exact step-by-step pipeline. First, they load the raw recordings. Then they apply a bandpass filter from 1 to 30 hertz just to clean up the signal. Step 3, they zoom right in on 3 very specific motor channels, C3, CZ, and C4, because those represent the primary spots for planning movement. And finally, and this is absolutely key here, they compute the analytic signal using a Hilbert transform. I know that sounds complicated, but basically this math creates a normalized view of these quick jumps in motor activity. It literally draws a sort of envelope around the data so we can clearly spot the peaks of coordinated action.
Now, what is absolutely fascinating is what they do with those extracted metrics. They track 5 main things. They look at the total count, the density per minute, and the average duration of the events. But it's these last 2 that are absolutely crucial: the mean inter-event interval, which is basically just the average waiting time between consecutive events, and the IEI coefficient of variation. That last one, the coefficient of variation, that serves as a direct index of how regular and stable the brain's timing actually is. It tells us not just if the brain is syncing up, but how consistently it's holding that beat.
Let's actually ground this in the real data from the study so you can see what I mean. Take a look at the difference between subject 1 and subject 2 here. Subject 1 has a super high event density, 145 events every single minute. And because they're firing off so many events, their waiting time, that mean IEI, is really short, just 0.38 seconds. Plus, their variability, the CV, is a really low 0.29. But now look at subject 2. Their event density drops way down to 97. And because of that, the time waiting between events jumps up to 0.61 seconds, and their timing variability spikes to 0.41. To put that into perspective, the data is clearly showing us that brains with a higher density of events maintain a much tighter, much more stable rhythm.
And that brings us to section 4, the threat of timing fragmentation, when the symphony fails. You know, every explainer kind of needs a villain, right? Well, in the story of the brain's timing architecture, the villain is this disruptive force that tears apart our delicate temporal coordination. The study points out a very specific pattern of warning signs. If an EEG shows low event density, combined with large interval variability and long waiting times between synchronization events, that is a massive red flag. And honestly, here is the scary part. According to traditional, old-school EEG measures, this exact same brain might show completely normal power levels. The volume is still loud, so a standard test says, hey, everything's perfectly healthy. But secretly, its temporal organization is suffering severe disruptions.
And this perfectly illustrates a core concept the researchers call timing fragmentation. Basically, this is a state where those vital neural integration events become sparse, irregular, and just really poorly coordinated. Going back to our orchestra, the instruments are still blasting, they're loud, but the musicians have completely lost the conductor's beat. They are totally out of sync.
So this brings us to a really critical pivot point in our explainer. We've been looking at raw data from a healthy motor cortex, and we've seen exactly how this timing fragmentation shows up in the math. But what does this actually mean for a real living human being? What happens to a person when this incredibly delicate timing architecture systematically starts to fail?
Let's find out in Section 5, Rethinking Neurological Diseases, a New Perspective on Pathology.
The clinical implications here are, quite frankly, paradigm-altering. We're looking at a massive contrast. The traditional view for a lot of neurodegenerative diseases sees pathology almost entirely as progressive neuronal loss, literally just the physical dying off of brain cells. But this SEBJ framework, it offers a radically different perspective. It views these conditions as a gradual disruption of the brain's large-scale timing architecture. The theory proposes that as your neurobyte density goes down and your timing variability goes up, that large-scale coordination just falls apart. And it's that specific lack of coordination that might eventually manifest as the deficits in cognition, memory, perception, and motor control that we currently label as Alzheimer's or Parkinson's disease. Which leaves us with this absolutely fascinating conclusion straight from the source. Brain disorders may be understood not merely as losses of neurons, but as progressive failures of timing architecture. It really forces you to ask, is the true essence of a healthy mind just found in the physical cells themselves? Or does it actually live in the invisible, perfectly synchronized rhythm that those cells create together? It's a huge question, and one that is absolutely going to drive the next generation of neuroscience. Thanks so much for joining me for this explainer, and as always, keep questioning how things work.